We are Team 31, and this is our final update on the RSNA pneumonia detection project. Pneumonia is one of the main causes of death for children under 5 years of age around the world, and it's even for highly trained doctors, it's hard to diagnose in a timely manner. So our project is to detect initial stages of pneumonia from X-ray images, and this project can be split up into object classification of whether or not an image has lung opacity, and if it does have one, then it's image detection of where it is in the picture, and our focus is going to be on that second task. And our data comes from the Kaggle RSNA Pneumonia Detection Challenge with almost 30,000 unique DICOM image files, some with lung opacities, some without, and then CSV files that signify which ones have the opacity. And if they do, then the variables for the bounding boxes such as the location and size. And here you can see the class distribution for this data and then the patient demographic distribution.
So talking about the model, we have implemented two different architectures. The first one is a faster RCNN and the second one is RetinaNet. So the RetinaNet is the one-stage detection while the faster RCNN is the two-stage detection, and both of the network architecture uses the backbone network. So we used three different backbone networks. The first one is ResNet 50, the second one is MobileNet V2, and the third one is VGG16. So VGG16 suffers from the vanishing gradient problem, and the ResNet 50 solves that problem, while the MobileNet V2 is the lighter network that uses the less parameters. So now let's talk about the model results.
Okay, so these are the results. Basically, this is, I guess, our method for evaluating the results of the performance of the model. So in the Kaggle competition, the results were evaluated as basically the mean average position at various IOU thresholds from 0.4 to 0.75 with a step size of 0.05. And so basically the formula for that can be seen here in the slide. And so we used a baseline model of a faster RCNN implementation with the ResNet 50 backbone. And so that was the model that we compared against with our different implementations of the faster RCNN as well as the RetinaNet. And so then in the next slide, we can see the results from the mean average position on the validation set. And so basically we can see that the best results were actually from the baseline model, which was the ResNet 50 backbone, faster RCNN. The worst results were with the RetinaNet with the ResNet 50 backbone, and the faster RCNN was about the same as the ResNet 50. And so in terms of training time for the models, the fastest one was the RetinaNet. The faster RCNN achieved 16 minutes per epoch for the ResNet 50 and about 8 for the MobileNet. And so then moving on to the graphs for the actual training and validation position. So this is the baseline model. And so this baseline model, you can see basically the results from the validation precision were the best ones. They achieved about 0.24 precision, and it was basically increasing as the epochs went on. So the next model was the MobileNet model with pre-trained backbone. So this model was pre-trained on the COCO data set. And so basically the weights from the COCO data set were used to try and facilitate the object detection test that we had. Basically, we were hoping that by using transfer learning, we can basically take these weights from the model and use them to initialize the weights for our new model for this new object detection, even though it's different classes of objects. And so then the next model that we tried to test on was a MobileNet V2 backbone for the faster RCNN, but this one was not pre-trained. And so basically you can see that the results are worse than the previous model, which was pre-trained on the COCO data set, even though the results were not as bad as we expected, but they still, I guess that might show that the weights from the COCO data set might have not helped as much because the data sets are not very similar in terms of the different classes. And so then the next model that we tried testing was a VGG16 backbone with a faster RCNN. So this one actually seemed like it was promising. It showed results from like 0.2 to 0.3 for the mean average precision validation, but this one oscillated all over the place. We're not sure what the reason for this was. It's something that we would have to further explore, because basically it might be just that we're implementing it incorrectly. And so then moving on to the last model that we tested on was the RetinaNet with the ResNet 50 backbone. And so for this one, the results were a lot more consistent in terms of it was increasing basically as time went on. but the results were definitely not as good as the other models, the faster RCNN models. This might be also due to the way that we implemented it, or that might just be the way it is. So one thing to note is that this one was a lot quicker than the rest of them because the RetinaNet is a single stage detection framework, while the faster RCNN is a two-stage detection framework. And so then in conclusion, basically our results show that even though we were not able to get results as good as the baseline model, which was the faster RCNN with the ResNet 50 backbone, we did still achieve interesting results. We showed that the mobile net was a lot quicker to train. This is due basically to the way that the model is defined. It uses separable convolution, separable depthwise convolution, and also show that the single shot detection frameworks are a lot quicker than the double, basically the two-stage detection frameworks, even though the results were not as good. And so thank you.